And now it's time to pass to like demonstration as well, and of the different services. This we divided the service into the related SDG. So we go first with the SDG 13, climate action, and in 1 hour almost, there will be 3 presentations from the service one on GHG emission from forest fire, and on service 2 on heat health risk assessment, and the last one, it's the service 3 on affected buildings and people. And sorry. Okay, good. It will be later on after the break. So, I leave the floor to Chiara Aquino. Chiara is working at CMCC with us, and he led the development of the service on GHG emission in collaboration with other experts in the consortium.
Thank you, Manuela. Hi all. So why do we choose this particular indicator? We know that the direct greenhouse gas emissions from forest fires must be reported under the UNFCCC and the Paris Agreement as part of national greenhouse gas inventories. However, at the European Union level, this is not reported in a standardized way, as the methods in which they are calculated vary between countries. Also, crucially, the data is not spatially explicit. With that, I mean it is not a geo-reference. We have most of the time CSV, so tables showing just the sums of greenhouse gas emissions in a year. We do not know exactly where the fire happens and how much it emitted. And also timeliness is a critical issue for this indicator, as it is up to 2 years from the reference time. Also, there is an issue with the methodology in itself, as we have strong uncertainties with the combustion completeness measurements and availability of the fuel. For example, in Italy, CO2 emissions from forest fires are estimated by assuming that all the forest biomass is burnt, is completely lost. We know that this is a conservative estimation, because not all the load available, so not all the volume of the forest disappears during a fire. This approach is considered in the IPCC framework a tier 1 approach, which is the most general one, and also in some ways also the most simplistic one. In the IPCC reporting scales, we have from tier 1 to tier 3, and obviously the advance requires more sophisticated data, more complex models, going towards tier 3. So it was mentioned before that the pilot initially was developed in Calabria and the Cosenza province. This was chosen because it's one area in Italy that is quite subjected to forest fires. In the period here between 2001 and 2020, 6% of the forest decrease, and mostly was due to forest fires. However, since we were looking at using georeference data and remote sensing, we realized quickly that we had the ability to do this for the whole country. And so we did extend all the results to the entire country. We could retrieve the data not just at the level of the Cosenza province, but at multiple national, subnational scales. So multiple provinces, municipalities, and also at the level of the whole country, as I will show later in the demonstration. So how did we do that? We decided to refine the IPCC methodology first to account for the proportion of biomass that is lost during combustion, and secondly, and crucially, we use remote sensing data from the Copernicus mission to increase the timeliness, the accuracy, and to make this methodology scalable to other regions. So in the team, there was myself, Manuela, for the scientific part, and Alessandro and Gishno that worked on the implementation of the service on the platform. So since quickly this service became something of its own, we decided to call it FireTrace, which stands for Forest Fire Framework for Tier 3 reporting and accounting of country-level emissions. So currently, the methodology and the work that we put into this is under review as a paper at the Nature Communication, Art and Environment. Finger crossed that it goes well. The aim of this service, FireTrace, is to provide a solid mapping tool for the national statistical officers and policymakers. As I mentioned before, really at the core of this service is to develop a workflow that is replicable in other settings, that is scalable, as it is based on Earth observation data. I said this before, but again, I would like to stress that what we aim to do was really to increase the temporal resolution, to reduce the timeliness that is a critical lag in this type of data set. Obviously, with the increased temporal resolution, we also focus on improving the spatial scale of the measurements, providing geographically explicit data. And eventually, we worked a lot also on the scientific research, improving the current methodology in estimating greenhouse gas emissions and also their accuracy. So this figure summarizes the methodology. The way this is calculated is based on the IPCC methodology, which is basically the equation that you see on the top. We have the multiplication of 4 factors, the burn area A. This comes from the FIS product, which measures burn area all over Europe and the Mediterranean regions. In the platform, the users can decide which year they would like to retrieve and the area of interest. And as I will show you in a bit, the area of interest can vary from the municipal level up to the entire country. Then we have B, the biomass. This is actually in situ data. We decided to use the National Forest Census in Italy, which provides in situ measurements of biomass for stratified biomass, which with that I mean for litter, for live trees, dead trees, fine wood debris, so different strata of the biomass present in the forest. From that, we were able to retrieve the biomass for each Italian region, divided by 19 vegetation species, so different types of trees, species basically. So this data is not a georeference. We have like an average value per region. To make it a georeference, we had to link it with an Earth observation-based product. For this, we use the 𝗙𝗏𝗏 level 4 product, which is a particular product that has been refined for Italy. So in this way, we have explicit biomass measurement in each area that we are measuring. Then factor C, this is the combustion. I'm going to talk about this in the next slide, but what we did was developing our own combustion model and then link this with another product from FIS called fire severity. So in each burn area that we retrieve from FIS, we also have a measurement on how severe was the fire. And we will link to our model the amount of biomass that is combusted. And finally, we have D. D is emission factors. They come from databases, the IPCC and the MEP-EIA mainly. So just a brief word on our combustion model, because on this we actually invested quite a bit of time for research. We developed our own combustion model for Italy, making this a new piece of research. So what we did was using, I mentioned before, if you remember, the biomass measurement from the forest census. We have data from 2005 and 2015, sorry. So we looked at the difference in biomass over this time. Then we check which one of these plots fell into an area where there was a fire. This comes from the ESA fire CCI layer that is also measuring burn area. And of the plots that fell in the fire, we retrieved the Landsat Delta NBR index. This is an index that measures the severity of the fire. So we saw the severity before and after. And on the right, I think it's the right, yes, it's the right. We developed like a correlation between the burning efficiency, which is the difference in the biomass between 2005 and 2015, and we linked that to the burn severity, which I said we took from Landsat data. And we did that for two main bird species, broadleaf and coniferous forests. Unfortunately, not a lot of plots in this time frame fell within an area with a fire. So this was one of the main limitations of having enough data, but that's a limitation with in situ data, always. And then from this correlation, we could derive 4 bird categories that corresponded to the same categories in the FIS fire severity layer: low severity, moderate low, moderate high, and high severity of fires. And from this, every time that we were looking in a burn area, we could connect the severity of the fire to the amount of biomass that was lost. So the 3 key points with this service are first, the transferability. So the pilot has been designed to progressively free the workflow from the field data. With this, I mean the way that ISPRA, that reports on the national level the greenhouse gas emissions, to get to the burn area, they use the Forestry Corps measurements in the field. So now from that you can understand it takes time to do those measurements. They are not always accurate, but mainly it takes time. With that, we decided to use remote sensing data because that's easier to access. And not only this is the reason why we address the timeliness problem, we can also allow the transfer to other regions, so beyond Italy, so we are free from the national in situ data. Then the scalability. It is really embedded in this workflow, the idea that this data can be scalable to multiple geographical regions. Not only political geographical boundaries, but also we can use boundaries that relate to biomes and ecosystems, so looking at ecological data. Another part that was very important was the validation. So we compared our results with 3 global satellite data sets on biomass burning emissions with Italian national inventory reports, the one that is done by ISPRA, and then 1 physical model. So these 3 bird categories, they work in different way. We plotted them, and our own data set is the one in black in the plot, which I just want to say briefly because I don't have time to elaborate. But we get like a sort of midway between the global satellite data set that are very coarse resolution compared to our own measurements, but less than the Italian National Inventory report. But remember, I said that that was a conservative estimate. They are overestimating because they consider biomass to be completely burned. So what we see is what we expected. So an important part of this project was the core design. There was an initial questionnaire, and I'm quite happy to say that we really incorporated all the necessities of the users into the service. Actually, the service is like this because the users contributed and they made a specific request. So it is really what Francesca was talking about with the agile methodology. So for example, there was a need for improving the temporal and the spatial scale, and that's what we've been addressing. The need to use other land cover definitions that were related to remote sensing data to measure in the LULUCF, and this is what we have done by using Korean land cover. So all of that has been integrated in the service. Our stakeholders were the Forestry Corps, the Italian Forestry Corps, the Italian Institute for Environmental Protection and Research, ISPRA, ISTAT, of course, and the University of Sassari. Midway in the project, we had a stakeholder workshop hosted by ISTAT in Rome, which was really crucial to change the direction in the way we were calculating the combustion model, because we had really important suggestions there on how to proceed in this sense. Then, as we developed the platform, we had as the champion user ISTAT, 𝗙𝗏𝗏𝗏𝗏 in reality, that I really want to thank for his really insightful comments that improved really the platform and the way that we were showing the data. And we had as validation users also the ECMWF, And so we had this uptake webinar where all these validation users discussed also the general indicator and these findings. So we have a front-end and a back-end version, but I would like you to see a quick demo of the front-end. Yes, okay. So once you access our service to the platform, you can select the year. Here we have from 2018 to 2023. The user can select the region, the province, the municipality, if they want. I chose Cosenza just because it was the first, the first province we chose in the beginning. So you can zoom in and out on the area. You can see the burn area, so where the fire happened, with the breakdown of the different contribution in greenhouse gases from the different type of vegetation species. So what can you do? Apart from visualizing, you can download the data. You can download it as a table that contains every single fire event with all the emissions broken down by gas species, with all the information on the vegetation type, and the standard deviation for each measurement, because that's also fundamental to keep. Also, you can download the data as a shape file and process it in your own GIS software if you would like to do more processing and visualization with your data. Yes, so this is just yeah, the main functionalities. You can run the service for the entire country. This is what I'm sharing here. And again, you can download it on the entire country. So that's what you can compare, for example, to the national statistical indicator. So just move forward a bit. Oh, okay. So yes, the main features of this service. FireTrace really offers a file-level resolution. I want to stress that this is a big achievement compared to the way this indicator is normally reported. As it is, as I said, it is normally reported as a sum of the total emissions. Okay, I'm going. Yes. Instead, here we can really get the spatial explicit information, so the single event, and check the type of forest affected, the amount of gases, the amount of greenhouse gases, and so on. Also, we can apply we can use this data for ecological applications, and we can see, for example, as expected, that Mediterranean forests are the largest contributors of greenhouse gases by biome. We can look at the level of ecoregions. Depending what kind of data we have, we can break it down and extrapolate the results. Maybe also for understanding patterns, so for further scientific research as well. For policy and statistics, we can get stats by looking at this data. So, for example, I found out that between 2018 and 2023, there was an average of 109 kilometers square of forest area that burned each year in Italy. This is equivalent to 50,000 football pitches of forest that is burned every year. If we look at the greenhouse gas emissions, we have an average of 1,000 gigagrams of CO2 equivalent every year, which is what 700,000 cars emit every year. So this kind of results that can be translated in something understandable by the public, you know, is something that we can also get out from this tool. You can look at the time series, so over time, how this change. We can break it down by the different forest classes. We have beech forest, broadleaf, chestnut. So again, interesting for the ecological application and research. So what were the challenges? The first challenge is that in situ validation is not possible for this kind of indicator. This is not just our problem. Like everyone working on this topic knows that there is no measurements of greenhouse gas emissions during a fire. Nobody goes in a fire and measures. There are other issues, more urgent issues to take care of in that moment. So the only thing we could do, as you've seen, was to compare with other data sets. So we will never know the actual true value, but we can see if the data is consistent. And there is an interannual trend that we can see that it's it works because we compare that to other trends from the different data sets. Another problem is the combustion model. You've seen that we developed it for Italy because that was our case study. However, if we want to develop this indicator for another country, we shouldn't use the same combustion model. We should develop one for, like, hopefully for the entire Europe. We should find a way to generalize that. And another issue is about the way we get biomass. So we decided to use the in situ data because that could be more precise than using the remote sensing product. However, when we compare that to the ESA product, the ESA product on biomass, we notice that our data was higher, was much higher, actually double the value. Why is that? We went to look into the data set, and we realized that, first of all, we didn't take care of the different forest management type in Italy. So in Italy, we have high forest, which has higher biomass, and then copies, which has lower. So because the data set only shows biomass data for high forest, we were considering all the data we were getting as the highest biomass forest. So that's why we have an overestimation. Another problem is that, I mentioned it before, the biomass data is not geographically explicit, the one that comes from the forest census. They provide averages per region. So if an area has been degraded, for example, then we don't know that. We consider that area always has having the average biomass per region. So this is something also to reflect on if we want to improve this tool. In terms of exploitation and sustainability, I think I've said quite a lot already, but to summarize, we provide spatial explicit data to national, supranational authorities to support the indicator, which is the SDG-13. We have tools and visualization outputs, as you saw. We have our own Earth observation-based fire severity model and biomass loss estimator. And we provide greenhouse gas emissions as a geodatabase at multiple scales, both in a shapefile and CSV format. And we have an interactive user interface for the greenhouse gas emission analysis. As potential uptakers, we looked into, obviously, ISPRA, the Italian Forest Services, so the stakeholders, statistical agencies, municipal and land use planning units, researchers, NGOs, and so on. We have a policy brief completed for this service. So we hope that there will be a long-term integration into monitoring systems for greenhouse gas emissions. The final thing I want to say is that this workflow was developed in a very modular way. This means that if there is a new data release, if there is new research done, from the point of view of the code, it can be modified without changing the whole architecture. Okay, and the data is available on GitHub, so everything will be open. And yes, these are, I guess, this is all. So thank you. Please, if you have any questions.
Thank you, Chiara. A question for Chiara. Yeah.
Well, first of all, thank you for the presentation. That was super clear, even though I'm not from this field. One question is that, as you mentioned, that from in situ validation is not possible for very obvious and understandable reasons. But how off do you expect to be, given that this validation is not possible? Assuming if this validation was possible, how off would you be with respect to the measurements that you make, which are not in situ? Do you expect that there might be a huge difference, just theoretically speaking?
Yes, so we did a comparison between the data that we obtain every year and the data that is already available. So this comes from mainly using satellite data. We have 3 global data sets, but the resolution is much different from ours. So also I had to harmonize that data. So I had to actually break it down, because they were using different emission factors, they were using different land cover definition. So I tried, when I did the comparison, it wasn't such a trivial operation, because I had to make sure that we were using the same land cover, the same emission factor. The only thing that would be different is how they were retrieving burning area, and also how they were calculating the combustion itself. That is one of the most critical factors. So I don't know if you meant that, like, if in terms of like getting in situ data, you need probably to organize a campaign of measurements, just
but then do you think that would help, in the sense that you might have a huge difference in the accuracy with respect to the method that you used? Theoretically speaking.
Theoretically speaking, I'm not sure, because as you saw, we all when you do the comparison with the other products, we never measure the same thing. There are always differences, because the 4 factors, the area, the biomass, each of them has its own uncertainty and its own variation. So I would expect the differences, of course.
Okay. And second and last question, instead of the fire CCI data for burned areas, why did you not use MOODIS, for example? Is there a reason for that? Or because I know there are some issues with the MOODIS burned area product that they produce. So if you had a reason to use the fire CCI instead of MOODIS, because it's better in some way, if you could comment on it.
So for the project itself, for the workflow, I used FIS. FIS, apart that it provides that fire severity layer, which is very fundamental for this. I think it's also because it's updated more frequently, and it's a continuous monitoring product. So that is, and actually it's not just MOODIS. From 2019, they use Sentinel-2, so the resolution is much better. I use the fire CCI only to develop the combustion model, and that's because I was looking for data for 2005. So MOODIS the FIS product didn't give me data so much back in time.
Yeah, because I mean, with MOODIS data set, at least one of the obvious problems is the uncertainty in the burned areas. It could be as large as 7 days, as far as the data that I've seen, which if you correlate it with the fire danger index, for example, it doesn't make any sense to use a fire danger index like 7 days before. So, I mean, just comment. So I was wondering if, for example, fire CCI could resolve this problem in the sense of having a more accurate date for the burned area. So that's what I was curious about. But all right.
And another reason why we use and we are focusing also in ESA CCI fire products is because we are testing the use of new products for mainly biomass estimation from new project, and because we are part of the RECAP, that is the regional reporting of carbon stocks for Europe, and so we are making synergy with the people working on ESA fire CCI products. So that's also why we try to update the future development of this service in this frame of the ESA CCI initiative.
Thanks.
Thank you, Chiara.